This episode examines how water utilities translate infrastructure into reliable service. We draw only on documented guidance and studies in the episode evidence register. Each chapter separates observed facts, working assumptions for design and planning, illustrative examples, and concrete recommendations grounded in cited material. Chapter 1. Reliability as a Service Outcome. Observed fact. Federal guidance and industry research frame reliability as an outcome that follows from systematic asset management, inventorying critical assets, assessing condition and performance, and planning maintenance, repair, replacement, and funding in a lifecycle context. Stated assumption. For planning purposes, a utility defines reliability in terms of continuity of service, compliance with service standards, and acceptable levels of risk to public health and the environment. This aligns with asset management objectives, but is a utility decision to be made locally. Illustrative example. Imagine a distribution system where repeated main breaks cause intermittent outages and customer complaints. Treating reliability as an outcome means moving beyond reactive repairs to a structured program that links pipe condition, failure likelihood, and the cost and timing of interventions to preserve service. Recommendation. Frame reliability explicitly as a measurable outcome in the asset management policy. State desired service levels, identify metrics that reflect those levels, and link investments to measured gaps. Use the EPA Asset Management Framework as the organizing template for those policy elements. Chapter 2. Asset Inventories and Criticality. Observed fact. Authoritative guidance lists inventorying assets and identifying those that are critical as a foundational asset management activity. Criticality ranking supports prioritizing maintenance, rehabilitation, and replacement decisions. Stated assumption. A practical inventory includes not only physical attributes such as material, size, and age, but also functional data such as redundancy, consequence of failure, and customer impact. The assumption is that consequence matters as much as condition when determining criticality. Illustrative example. An inventory that lists two similar pumps, but notes that one pump is on a single feed process that would stop on failure, is likely to assign higher criticality to that pump, even if both are the same age and manufacturer. Recommendation. Build asset inventories that combine physical and service impact fields. Use criticality scoring to move from a long list of assets to a prioritized register for inspection and intervention. Document scoring rules so decisions are auditable and repeatable. Chapter 3. Condition, Consequence, and Remaining Life. Observed fact. Institutional research emphasizes that estimating maintenance needs and failure probability requires understanding an asset's condition, its remaining useful life, the consequences of failure, and renewal options and costs. This understanding is the basis for improved investment decisions. Stated assumption. Condition assessment programs will be imperfect and probabilistic. Condition observations, inspection frequencies, and diagnostic techniques produce degrees of confidence, not absolute certainty. Planning must therefore use risk-informed estimates rather than deterministic guarantees. Illustrative example. Two buried pipelines may show identical age records. On excavation, one exhibits severe corrosion, while the other is largely intact because of differences in soil chemistry and loading. Condition data, not age alone, changes the decision from replacing on schedule to repairing one and monitoring the other. Recommendation. Adopt condition assessment methods appropriate to asset type and consequence. Record condition data and derive remaining useful life estimates with associated uncertainty ranges. Use that characterization to rank renewal candidates. Condition and consequence are central to prioritizing interventions. Chapter 4. Preventive and Predictive Maintenance. Observed fact. Literature and guidance identify preventive maintenance, meaning scheduled activities, and predictive maintenance, meaning condition-triggered activities, as two principal maintenance strategies utilities may employ. Selecting the right mix depends on asset behavior, data availability, and cost. Stated assumption. Predictive maintenance requires better data and analytics than preventive maintenance. Moving toward predictive approaches yields efficiency only when data quality and analysis provide reliable lead indicators of failure.
Illustrative example. A pump fleet managed solely on run hours, a preventive approach, might be over-maintained for pumps that operate under benign conditions. Conversely, vibration monitoring, a predictive approach, can flag bearing wear and trigger targeted repairs before catastrophic failure, reducing downtime and spare part consumption. Recommendation: evaluate assets by failure mode and data readiness to select preventive or predictive approaches. For high criticality assets with detectable precursors, invest in condition monitoring and analytics. For low criticality assets with predictable degradation, scheduled preventive maintenance may be preferred. Tie choices to condition and criticality data captured in the inventory. Chapter 5. Failure modes and intervention choices. Observed fact. Research shows that decision-making about repair, rehabilitation, or replacement must consider failure modes, costs of options, and the consequences of inaction. These variables are central to determining appropriate renewal solutions. Stated assumption. Intervention choice is a trade-off among upfront expenditure, expected remaining life extension, residual risk, and operational impacts. No single intervention is universally optimal. The right choice depends on asset criticality, condition, and the utility's financial constraints. Illustrative example. A corroded valve in a low-pressure branch may be cheaper to maintain repeatedly than to replace immediately. By contrast, a failed valve on a high-pressure trunk that risks service coverage may warrant replacement despite higher immediate cost. Recommendation: for each high-priority asset, document viable intervention options, associated costs, expected life extension, and change in failure probability. Use that structured comparison to make transparent renewal decisions. Chapter 6. Data Quality and Organizational Handoffs. Observed fact. The U.S. Government Accountability Office reported that accurate data can help utilities understand maintenance, rehabilitation, and replacement needs, and improve asset decisions. But many utilities face challenges collecting data and integrating information across departments. Stated assumption. Data systems and organizational processes are as important as technical inspection methods. Without clear handoffs and data governance, condition data will not translate into consistent decision-making. Illustrative example. Field crews collect inspection notes on paper. Record staff manually transcribe observations into a database weeks later. In that interval, priorities shift, and the inspection may not inform the next budget cycle because the data are not integrated into planning tools. Recommendation: invest in a data governance plan that defines owners for inventory fields, inspection schedules, and condition updates. Prioritize systems integration for high-priority asset classes, and scope pilot projects around the most impactful handoffs first. Chapter 7. Renewal Economics and Risk. Asset management guidance links decisions to financing and lifecycle costs. Research frames investment prioritization as contingent on understanding lifecycle costs, failure probabilities, and consequences. Both position renewal economics as central to program viability. Stated assumption. Fiscal reality constrains choices. Utilities face trade-offs between deferring capital replacement and accepting higher operational risk and maintenance costs. A transparent economic framework is essential for defensible decisions under constrained budgets. Illustrative example. Rehabilitating a pipeline may cost less in the short term than full replacement, but if rehabilitation yields only a short remaining life and frequent repairs, the longer-term life cycle cost may be higher than replacement. Comparing present value or life cycle cost outcomes clarifies those trade-offs. Recommendation: integrate life cycle cost estimates into renewal decision matrices and make explicit the risk tolerances applied, such as acceptable outage frequency and environmental consequence thresholds. Lead financing plans to prioritize renewal. Chapter 8. A Practical Reliability Program, Implementation and Decision Framework. Observe fact. The sources collectively define core elements of an asset management program: asset inventory and criticality, condition and performance assessments, intervention planning, maintenance strategy selection, financing, and organizational alignment. Each
A stepwise implementation is more achievable than attempting full coverage immediately. Pilots that address the most critical assets and the toughest organizational handoffs can demonstrate value and build capacity. Illustrative example. A utility begins with a pilot that inventories all pumping stations feeding a primary treatment plant, ranks them by criticality using redundancy, process risk, and customers served, performs condition assessments on the top-ranked 3, and compares 3 intervention options for each. Continue preventive maintenance, install condition monitoring instrumentation and move to predictive maintenance, or schedule staged replacement. The pilot documents cost estimates, expected remaining life under each option, and projected service reliability outcomes. It serves as a template for expanding to other asset classes. Recommendation, implementation, and decision framework. Step 1. Inventory and criticality. Create a minimum viable asset register for the highest impact assets and document criticality scoring rules. Step 2. Condition assessment and remaining useful life. Select methods appropriate to failure modes, record condition with uncertainty bounds, and estimate remaining useful life. Step 3. Failure mode analysis and options. For each high criticality asset, list failure modes, quantify consequences, and establish feasible interventions with expected life extension and costs. Step 4. Maintenance strategy selection. Choose preventive or predictive maintenance based on criticality and data readiness. Prioritize predictive investments where monitoring yields timely, reliable lead indicators. Step 5. Economic evaluation and funding. Compare lifecycle costs and risk reduction per dollar across options, and align decisions with finance strategy. Step 6. Data governance and organizational handoffs. Define data owners, inspection workflows, and integration points between operations, engineering, and finance. Address integration challenges by piloting handoffs for the pilot asset class. Step 7. Review and scale. Use pilot results to refine scoring, condition assessment frequency, and data collection standards, then scale to additional asset classes. Engineering trade-offs explained. Data versus decision speed. Collecting high-quality condition data improves targeting, but requires investment and time. The trade-off is between acting on imperfect data quickly and delaying action to improve confidence. Preventive versus predictive maintenance. Preventive maintenance is lower data and easier to execute, but can waste resources on low-risk assets. Predictive maintenance targets interventions, but requires sensors, analytics, and data flows. Short-term cost versus long-term lifecycle cost. Rehabilitation can defer capital expenditure, but may increase cumulative costs and risk. Organizational complexity versus technical sophistication. Advanced condition monitoring can improve results, but stresses workflows and data governance. Closing recommendations. Start with a scoped pilot focused on the most critical asset class. Use it to validate condition assessment protocols, data handoffs, and cost estimation methods before scaling. Document decision rules and criticality score so investment choices are auditable and repeatable. Tie decisions to lifecycle cost and risk metrics. Prioritize data governance and integration where it unlocks the largest decision benefits. Accept uncertainty and manage it explicitly. Estimate remaining useful life with uncertainty bands and use risk-based prioritization rather than deterministic schedules. Epilogue. The authoritative documentation supports an approach that links inventory, condition assessment, criticality, maintenance strategy, economic evaluation, and organizational processes to achieve service reliability. Demonstrating outcomes in varied contexts requires more applied cases and updated studies specific to asset types and regions. The practical pathway is to implement pilots, measure outcomes, and iteratively extend the program using this framework.
Reliability is not a single maintenance task, and it is not a promise that every failure can be prevented. It is a decision system that makes service objectives, asset condition, consequence, uncertainty, and funding constraints visible at the same time. A useful program, therefore, starts small. Select the asset class where failure would matter most. Define a minimum viable register, and agree how criticality will be scored. Then test the inspection method, the handoff from field crews to record staff, and the way condition information enters the investment process. The pilot should produce evidence about the process itself, not only about the asset. When a decision is made, preserve the reason for it. Record the condition observed, the failure modes considered, the alternatives rejected, the expected life extension, the risk tolerance, and the assumptions behind the cost comparison. A future operator should be able to understand whether a decision remains valid when the asset, the budget, or the service objective changes. The practical test is simple. Can the utility explain which assets are most critical? What is known about their condition? Which intervention is preferred? And what uncertainty remains? If not, the next investment may need to be better information and better coordination rather than more equipment. By treating data governance, maintenance strategy, lifecycle economics, and organizational handoffs as parts of the same reliability program, the utility can move from reactive work toward defensible, measurable service outcomes.